Kenshi
Miyabe. Okay. Is that okay? I'm Kenshi Miyabe from Kyoto University. Today I will talk about a basis for tt-Schnorr randomness, and I when I see the definition of basis tt-Schnorr randomness first, one may not accept this. So I'll explain. I try to explain why this is the natural and right notion. So, so here's a summary. First, here's a law for Schnorr randomness, and it is equivalent to law for computable measure machine and computably traceable, but not equivalent to Schnorr trivial. And then subsequently, Franklin and Stefan show that Schnorr trivial is equivalent to law for tt-Schnorr randomness and computably tt traceable. And I show that another characterization. And in this talk, I will show you two other characterizations of Schnorr triviality. One is WDM reducible to the empty set, and finally a basis for tt-Schnorr randomness. Okay, so here's first we review the table. Maybe most of you know that the following is equivalent for a set. A is law for multi-roof random, and A is law for K, and A is K trivial, and A is basis for multi-roof random. And I heard other many characterizations for K triviality, but we focus only these four notions, and we consider Schnorr randomness version of these notions. Then let's consider Schnorr randomness version. First, we can define rawness for Schnorr randomness. I will do not give the precise definition, but and Schnorr triviality. However, these are not equivalent because there is a Turing complete survey Schnorr trivial CE set. This means rawness for Schnorr randomness is not equivalent to Schnorr triviality. And Franklin and Stefan show that following are equivalent. A is law for tt-Schnorr randomness, and A is computably tt traceable, and A is Schnorr trivial. So first we need to know the notion of tt-Schnorr randomness. What is tt-Schnorr randomness? First, recall that if a set is Schnorr random, if for all computable order H and computable martingale D, then D of the n bit of the prefix n bit prefix of x is less than or equal to h of n plus O1. Then if relativized to some set A, then we got this. So x is a Schnorr random if this inequality holds for all A computable order H and martingale D, tt below A, t Turing below A. So Franklin and Stefan introduced A tt-Schnorr randomness. So maybe terminology are different, but I call A. So it's a tt-Schnorr random relative to A if let D be a martingale, tt below A, and H need not to be tt, so computable order H for this inequality holds. So, and actually, so if A is computable set, then A-Schnorr random is equivalent to A tt-Schnorr random. But in general, these are different.
In the definition, is it? Well, in the one definition, it's A computable, H is A computable, and the other definition, H is computable.
Yes, because H can be replaced by tt below A, but it is actually computable. So we do not care about that. So here is so if A is computable, then these are equivalent. So A tt-Schnorr randomness is another relativization of Schnorr randomness. So this is another relativization. So we have another rawness notion for tt-Schnorr randomness. So A is low for tt-Schnorr random, they called tt low for Schnorr, but I prefer this. So anyway, so A is low for tt-Schnorr random if each Schnorr random set is A tt-Schnorr random. So this is not equivalent to low for Schnorr randomness. So we need to be care about tt. And
but you can write also each tt-Schnorr random set.
Each tt-Schnorr, yes. Each tt-Schnorr random is yes,
same as
yes, same. So maybe yes. And this notion is equivalent to Schnorr trivial. Oh, sorry. I will show you the definition later. And Dunning-Green, they show that rho for computable measure machine and it is computable traceable. I do not give the definition, but I show the so I gave the characterization of tt-Schnorr randomness by, of course, test and machine. And the test is called tt reducible measure machine. Then this is a counterpart result. So the proof is also very similar, just a little modification. We have this characterization. So let's go to the main topic. So basis for tt-Schnorr randomness. So first recall that. So this is the definition of a basis for Martin-Roof random. A is a basis for Martin-Roof random if there exists B such that A is T Turing reducible to B and B is A Martin-Roof random. And it is equivalent to rawness for Martin-Roof randomness. So what's the Schnorr randomness version? So consider a set A such that there exists B such that A is tt reducible to B and B is A tt-Schnorr random. So it's a natural definition. So it is equivalent to rho for tt-Schnorr randomness. Actually, no. But one implication holds. They show that if A is tt reducible to B, and B is a tt-Schnorr random, then A is Schnorr trivial. However, the converse does not hold. There is Schnorr trivial set that is not truth table reducible to any Schnorr random set. They also show that similar form by SNR reducibility, but of course it's not commonly accepted. So the question is, is there a notion such that the definition uses tt reducibility and the definition uses tt-Schnorr randomness, and notion is equivalent to tt-Schnorr triviality, and thus we can call a basis for tt-Schnorr randomness? Is the main question. Then I will answer this finally. But before that, I would like to explain characterization of Schnorr triviality via decidable prefix-free machine. First, let's recall that characterization of Schnorr randomness by computable measure machine. So what is computable measure machine? CMM, computable measure machine, is a prefix-free machine n such that the measure of the machine is computable. Then it characterizes Schnorr randomness. A set is Schnorr random if and only if complexity of respect to this computable measure machine is larger than n up to a constant. So Schnorr triviality defined by using this machine is, first we define reducibility. A is Schnorr reducible to B, denoted by like this, if each computable measure machine n, there is computable measure machine n such that this inequality holds. So intuitively, if B is compressible to some extent by a computable measure machine, then A is also compressible to the same extent. And Schnorr triviality is defined by A is Schnorr reducible to the empty set, so the bottom degree of Schnorr degree.
Which means what? So for empty set, Km is constant.
Km to n. So empty means this is 0, 0, 0, 0, 0, 0. So the first n bit, the Km of the n. So this is the definition of Schnorr triviality. And we have another characterization of Schnorr randomness by decidable machine. A machine M is decidable if the domain is computable. And recall that order is an unbounded non-repeating function. Then Bienvenu and Merkel show that A is Schnorr random if all decidable prefix-free machine M and computable order G, we have this inequality holds. So not n, but n minus gn. So almost n, but we can allow the little compressible. Then it's natural to ask, so can we use the machine, this machine, decidable machine, to characterize Schnorr triviality? We can. So first define reducibility. A is weakly decidable prefix machine, reducible to B. I'm not sure this is a good terminology, so I welcome your recommendation, suggestion. So denoted by like this. if each decidable prefix-free machine M and the computable order G, there exists another decidable prefix-free machine N such that this inequality holds. So we allow this part. This reducibility characterizes Schnorr triviality. First, I got that so A is Schnorr trivial if and only if A is WDM reducible to the empty set. But after that, actually, these reducibility are equivalent. So this means computer measure machine and prefix-free decidable machine are almost same power of compressive power. So we have many characterizations of Schnorr triviality, very similar forms. This is the definition of Schnorr triviality, and this is the explanation I got what I explained now, and traceable and another characterization, and all characterizations have the similar form. So for all computable something, there exists a computable something, then something. So how about consider the similar form for a basis for tt-Schnorr randomness? So because the following does not hold, A is low for tt-Schnorr randomness, then this. So multi-roof randomness version, actually this is very easy because A is low for multi-roof random, this A is basis for multi-roof random. This is because Kuchera-Gax theorem, there exists a multi-roof random set B such that A is reducible to B, and B is actually a multi-roof random. So we consider Schnorr randomness version of Kuchera-Gax theorem. That means computable martingale version for Kuchera-Gax theorem. So before that, recall the space lemma, but so first we consider a tt-Schnorr random for D. So we fix D, a tt martingale tt below A, and another we also consider tt reducible random for D. So then X is a tt-Schnorr random if X is a tt-Schnorr random for D, for each D. And this is the definition of a basis for tt-Schnorr random. A basis for tt-Schnorr random if for each martingale D, tt reducible to A, there exists a set B such that A is tt reducible to B, and B is a tt-Schnorr random for D. So B can depend on D. So that's the difference between from the usual definition of basis for Schnorr random, basis for tt-Schnorr random. And similarly, we defined a basis for tt reducible randomness. So it's a tt version of computable randomness, and main result is this. Following the equivalent, A is Schnorr trivial, and A is a basis for tt-Schnorr random, and surprisingly, at least to my surprise, A is also equivalent to A's basis for tt reducible randomness. I'm not sure why this is, but it seems. The proof sketch is like this. So what we want to show that is the most difficult part is computable tt traceability implies a basis for tt reducible randomness. So first, let phi be such that so d phi of a is a martingale. Then we need to construct b such that these condition holds. By space lemma, this condition is not difficult to maintain, but this part is actually difficult because D is not computable, not C. It is TT below A. So we need to put the information into B of A. But we need not use all information of A. So just B needs to construct B to construct A from B. We only need the wrong prefix of A. So this so if A is computable tt traceable, then this we can do this. So this implies holds. Just a proof sketch, but intuitively. Here is and again the summary. So Schnorr trivial is equivalent to rho for tt-Schnorr and computable tt traceable and rho for t traceable measure machine and another W2M reducible to empty set, and it is also equivalent to a basis for tt-Schnorr randomness. So at least this table was completed, but I don't know other characterization of k-triviality. So that is all. Thank you for your attention.
Any questions for the speaker? Not? Say the speaker again. Oh, sorry.
At some point you had this computable order G.
What was the G?
What happens if you say take not all computable orders but subclasses?
Oh, I see. It may not need it.
But det betyder for på normal time, det er ofte the same probably.
Oh, yeah.
Just slower, yeah.
Yeah,
If they're more powerful, then it can be more interesting.
Oh yeah, or that, yeah.
Okay, let's thank the speaker again.